Hi everyone. I thought I would record a video on Chapter 11 of Richard Hammack's textbook, Book of Proof. Chapter 11 is all on relations, so it starts with the definition, which I have on the screen in front of us, and then it talks about what it takes to be an equivalence relation, which is one of the most important concepts in all of modern mathematics, I would say. And then it talks about partitions and introduces the very important theorem that an equivalence relation, whatever that may be, partitions the set you're working in. So we'll talk about all of that. We'll spend most of our time on the exercises, but I'll introduce the main definitions and theorems briefly as well. So to start off, our first definition, a relation on a set A, is just a subset of the Cartesian product of A with itself. What that means is anytime you have an ordered pair, which is an element of this relation, you say x is related to y, and you kind of sketch that out, something along the lines of, if A is the set 1, 2, 3, then A cross A looks something like this, and a relation on this set could be, any way of highlighting ordered pairs within A cross A. So here's some random assortment of points in A cross A. A is the set 1, 2, 3. And these points constitute some relation which I could call R. In general, I think of relations as more general functions. This is not a function, of course, because functions can only have one y value for every x value. So that's why I say it's more general. It's like a function with a condition relaxed. So yeah, a relation can have a single y value having a single x value having as many y values as you like. In any case, let's try some of these exercises. So for exercise 1, I've laid out the following. We have the set 0, 1, 2, 3, 4, and we want to write out a relation that expresses the divides operation. Namely, when does one of these integers divide another of these integers? And illustrate it with a diagram. So again, we could sketch out, I'll draw this a little bigger. We could sketch out A cross A. So here's 0, 1, 2, 3. A only goes up to 4, so I'll stop there. Cool. So there's A cross A, and I want to know which of these integers divides which other integers. Let's ignore 0 for now, because 0 is a little difficult to think about. We'll circle back on that at the end. But I do know if I focus on the positive integers here, and let's just hone in on 1, I know it's true that 1 divides itself, 1 divides 2, 1 divides 3, and 1 divides 4. Right? Because that's just saying 1 is a divisor of all of those numbers. Right? 1 divides into everything. So, great. What that means is 1 is related to 1, 1 is related to 2, etc. Or if I write this as ordered pairs, 1 being related to 1 means 1 1s should be in this relation. 1 being related to 2 means 1 2 should be in this relation, etc. So I can put these points on here. I can say 1 is related to 1, 1 is related to 2, and 3 and 4. So all those ordered pairs can go in the plane, which represents A cross A. What about 2 dividing numbers? Well, 2 divides 2 certainly, and 2 divides 4. 6 isn't in here, so I guess I can't write 6, but just highlight everything that 2 divides, and then similarly 3 divides itself. 3 would divide 6, but 6 isn't in the set A, so we have that, and then 4 divides itself. So you get some nice pattern like that. No integer here is going to divide something lower than it, so this is all empty, of course. And then you have empty slots where, for example, here 2 does not divide 3, here 3 does not divide 4. Okay, let's talk about what happens on the axes, though, what happens with 0, because it's important to know divisibility rules when it comes to the number 0. So let's ask, does 0 divide 1? Well, this would be, I'll put a little question mark above this. This would be equivalent to, what does it mean for 0 to divide something? It means that thing on the right is a multiple of 0 for some integer n. But that's of course false, right? Because this is equal to 0 and 1's not equal to 0. So it's not true that 0, 1 is a point here, right? 0 doesn't divide 1. I colored it red to say it's not there, but let's just erase it. The same logic should hold for 0, 2 and 0, 3 and 0, 4. 0 is not going to divide any of those. However, 0 will divide itself. Why does 0 divide itself? Again, I can put a question mark. Well, that would be equivalent to saying 0 is a multiple of 0. And that's true, right? You could actually pick any integer n, and that would be a true equation. So 0 divides itself. And sort of for similar logic, it's going to be true that every other integer divides 0. Which is a weird phrase to say, because you always associate it with like, oh, I can't divide by 0. But something dividing 0, for example, 3 dividing 0, just means 0 is a multiple of 3. 0 can be written as n times 3 for some n. That's true, in particular, for the choice n equals 0. Okay, so I fill in the whole, this whole bottom line. And that should be everything. That exhausts all the options, so that's what the relation looks like. Again, it's not a function, because, you know, for example, this x value has 5 y values associated to it, but feel free to think of it as a more general function. We'll build up to actual functions eventually. All right, next exercise. Write the relation greater than on the natural numbers as a subset of n cross n using set builder notation. We can sketch this if we want. So again, you can draw a little Cartesian product. Of course, in this case, the natural numbers go on forever, so I'll put dot, dot, dot. Maybe I'll include 4 in here just to keep adding to it. Okay. What does this look like as a Cartesian product? Well, for some element n comma m to be in the relation greater than, that's a weird notation I just wrote, but sure enough, this is a relation, right? It tells me when one integer is bigger than another, and relations are subsets of the Cartesian product, so I can write that. That's weirdly valid. And this is equivalent to just saying n is greater than m. So it's sort of like saying the x-coordinate is bigger than the y-coordinate. When does that happen? Well, for example, 2 is bigger than 1, right? So this is the point 2 comma 1, because 2 is bigger than 1. Similarly, 3 is bigger than 1, and 4 is bigger than 1. If I go up a level, 3 is bigger than 2, so that's 3, 2. That belongs to the relation, certainly. And 4 is bigger than 2. Keep going up. 4 is bigger than 3. And you can kind of guess that you'll build this, this sort of staircase here. Great, so we know what it looks like. Actually, drawing it out might be harder than just writing the relation in set builder notation. This relation, sorry, that should be greater than, huh? This relation greater than in set builder notation could be written as the set of all ordered pairs of natural numbers. So remember, ordered pairs are in the Cartesian product of n with itself, in this case. And I just want m greater than m. That's all it is. Right, it's basically just drop the relation right here. X-coordinate bigger than y-coordinate. Okay. And you can maybe take some time to think about, yeah, that does actually produce this graph here. Okay, exercise 3. Consider this relation, r cross r, so don't get confused between the different r's. Boldface r means the real numbers. So this is effectively r2, the plane. And then I subtract. What am I subtracting? Well, looks like the x and the y coordinate are the same. So it's sort of subtracting the diagonal. That's the line y equals x. Right, so here's the line y equals x within the Cartesian plane. And the relation is actually everything except for that. So you imagine it as the plane with that diagonal line deleted. The relation's in purple. Cool. What familiar relation on the real numbers is this? Well, judging from this, it's not exactly equal, or it's not exactly easy to see. It might be easier to see if we just wrote out, okay, so r is the real numbers in 2 dimensions minus this diagonal. And maybe I can play around with this set builder notation and get it to look like something nicer. This is effectively a complement in R2. It's effectively all x in xx in R2 such that, well, let's write it like this. All xx such that x is in R, and then I complement it, right, because we're actually doing R2 minus this set. But the complement, what does that mean? Well, let's think for a while. Let's leave the complement on here, and I'll write this a little differently yet again. The ordered pair x comma x could be rewritten as the ordered pair x comma y, such that x and y are real numbers. But that's not enough. I need one more condition. Right? If I left it here, that would just give me the whole plane. If I want it to be the same as the line above, x and y better be equal. Right, so these are now the same set, so it's reasonable why I put an equal sign between them. And now if I'm taking the complement, you maybe realize I can just complement this condition here. So instead, I can rewrite this as, so no complement anymore, just the set of xy, such that x and y are both in R, and y is not equal to x. And once we write it like that, maybe we see, just like we saw up here, right, remember this, the relation is sort of highlighted right there in the conditional part of the set builder notation. Same story. It's the not equals relation. So let's write that down. R is the relation not equal to. Cool. And now you can go back and convince yourself that, okay, the diagram makes sense for that. A real number is related to another real number if they're not equal. So if they're off this diagonal, that's all the purple region. So it works out. Okay. This one's a fun one. Given a finite set A, how many relations are there? Like, how many relations can you imagine? Let's suppose the cardinality of A is some natural number n. Then I know I'm looking at, we could sort of denumerate the elements of A as 1, 2, 3, all the way up to n. Maybe those aren't actually the elements. Maybe A is a set of matrices or something weird like that. But you can at least label them 1 through n, because you know there are n elements. So, okay, up to relabeling, this is fine. So this is sort of what I'm drawing for A cross A. I know my relation has to live in here. The key observation is then there are n times n, so n squared possible places I could put relations. in a way. You know, I could say, for example, this one I'm about to fill in. If I fill in this, that would mean 2 is related to n. Right, so that's one possible relationship between these integers, or these elements of A. Similarly, you know, I could fill in any of these holes and get a valid relation. Put dot dot dots in here as well. Okay. So I sort of imagine this as a pegboard. There's a pegboard with, in this case, n squared peg holes, right, n times n. And I can fill them however I want. Right? This isn't a function. I don't have to just do one per column. I can do as many as I want. I could do the empty relation, which is currently sitting here. That's a valid relation where I don't put any pegs in the holes. Or I could do, you know, the complete relation where everything is related to everything else. I'm not going to sit here and fill in all the circles, but imagine I did. Or anything in between. Right? So how many possible relations are there? Well, one way to think about this is to like turn on your binary brain and realize, you know, each of these can either be colored or not colored, filled or not filled. So there are 2 options for each, and if there are n squared peg holes, then there are 2 to the n squared possible relations on A. Right? Because it's like, okay, I have 2 choices here. I have another 2 choices here. Another 2 choices, another 2 choices. Another 2 choices, another 2 choices. I have 2 choices for each of n squared options. So that's 2 to the n squared. Right? Just multiplying 2 by itself, n squared times. Cool. All right. Next up, we get into the second section of the textbook where we define 3 properties that relations can have: reflexivity, symmetry, and transitivity. It turns out, I'll give a little spoiler, if you have all 3 of these satisfied, you're something called an equivalence relation, and those are massively important in all areas of mathematics. But for now, let's just talk about them separately. A relation's reflexive if every element is related to itself. That's what the formal logic says there. In terms of a graph within A cross A, reflexivity would mean the diagonal is completely filled. So whatever your set is, every element being related to itself means the diagonal is filled. Symmetry, on the other hand, is sort of like symmetry of matrices, at least when you graph it. Technically, the definition is, okay, if x is related to y, then y is related to x. What that turns out to look like is something like this. Anytime I have some sort of relationships on, let's call this the lower diagonal, so maybe I have that, then, and let me just add something on the diagonal, because why not? So here's my diagonal for y equals x. If this relation were to be symmetric, it would have to reflect on itself across that line. And you can sort of sit and think about why this drawing is equivalent to the formal logic definition here. Let me make sure I get this right. That looks symmetric to me, roughly. So yeah, if you've thought about it, then here's xy, say. So that dot being purple means it's in the relation according to my color scheme. So x is related to y here. If this relation's symmetric, I need y related to x. But guess what? Y comma x is what you get by reflecting across the line. Y equals x. So there's y comma x. So that's what symmetric relations look like, and that's why they're called symmetric, at least partly. Transitive is the transitive property we all know and love, that if x is related to y and then y is related to z, then x is related to z. transitivity is hard to draw, but hopefully it's something that's talked about enough in other settings that it's fairly familiar. Okay, so let's consider a relation and ask if it's reflexive, symmetric, or transitive. So the relation is x minus y in absolute value is an integer. This is a relationship on the real numbers, meaning x and y can be any real numbers I desire. First, is this reflexive? Well, let's see. Reflexive would mean that for all real numbers x is related to itself. Okay. Let's write out what that means. So pretty much when I'm proving reflexivity, symmetry, or transitivity, I like to write out the formal logic most of the time, just because this XRX notation can be kind of ugly to work with. So that would mean for all x in the real numbers, well, x being related to x would mean x minus x is an integer. But, okay, x minus x is 0. Absolute value of 0 is 0. And 0 is an integer. So this is just a true statement, but it's equivalent to reflexivity. Therefore, reflexivity gets a check. It is. Symmetry. Well, symmetry is actually an implication. So I can start with arbitrary x and y in the real numbers in this case. And then I can assume x is related to y. So let's start doing that. For all x and y in the real numbers, this is basically me saying, okay, let x and y be real numbers and assume x is related to y. What does that mean? Well, x being related to y means, so let's just write this out. Actually, you know what? I'm not going to do the formal logic. I'm going to write out all of this in words. So let x and y be real numbers, and suppose x is related to y. That is, we have the definition of x being related to y right here. Absolute value x minus y is an integer. Okay, my goal is going to be the reverse of that, showing that y minus x in absolute value is an integer. Maybe I'll write that down. Because if I show that, then that would imply that, write it like this, y is related to x. So that's my goal. How can I get there? Well, we're very fortunate in that y minus x in absolute value is the same as, let's factor a negative 1 out. So this would become x minus y now, in parentheses. But I have a negative 1 inside an absolute value, so that can just go away. It becomes positive 1. And I'm left with the absolute value of x minus y, which I know is an integer. That's exactly my assumption here. So, ta-da. In total, this is saying y minus x in absolute value is an integer. Therefore, y is related to x. So check, it's symmetric. Then transitive. This time I want to consider triples of things. So x, y, and z real numbers. And I want to suppose x is related to y and y to z. Okay, again, based on the relation, that means x minus y is an in absolute value is an integer, and y minus z, same idea. then the question becomes, what about x minus z? Is that an integer? And you can probably convince yourself that the answer is yes. Just think of some examples, maybe. The key is sort of if, let's say I use my hands here, if x and y are an integer distance apart, so here's x, here's y, and then y and z are an integer distance apart, then x and z are as well. Right, my thumbs are an integer distance apart. The annoying thing is x and y and z can come in like random orders. So there's a version of this proof where you sit down and show, like, for every possible ordering of x and y, transitivity still works. We don't necessarily want to do that. We could sort of just wave our hands a little and say, without loss of generality, suppose x is the biggest. So x bigger than y, bigger than z. Why am I allowed to assume that? Well, the integers x, y, and z are going to come in some order, so just relabel them until they're in this order. The only obstacle there is, why am I not considering whether x and y are equal, or y and z are equal, or x and z are equal? The answer is not obvious, but once you sit down and look at the relation, it sort of comes to that, oh, if there's equality here, then everything's dandy, right? Because we're hoping to prove that x is related to z. And, okay, let's assume one of these cases. Let's assume x was equal to y. Well, great. If I'm assuming x is equal to y, then this y here is actually an x. So x is related to z. Ta-da, I'm done. So I'm kind of ignoring that case because it's not too hard once you sit down and think about it. And so instead we're assuming all the real numbers are distinct and they have some order to them. Hopefully that's okay. Or hopefully you're amenable to that. Now, since I'm assuming that, I can just say, we said we wanted to look at x minus z in absolute value, but x is bigger than z, so x minus z will be positive. It'll just be x minus z without absolute value bars. And what can I do from here? I want to show this as an integer. Well, the inspiration comes from what I was doing with my fingers. You know something about this distance, you know something about this distance. If you add them together, you get the full distance. So let's do that. That's like saying x minus y plus y minus z. So if the picture doesn't make sense, at least maybe this does, that I'm adding 0. It doesn't change anything, but this is great because x minus y is an integer, and y minus z is an integer. Again, x is bigger than y is bigger than z, so I don't really need absolute value bars there. In any case, an integer plus an integer is an integer. So that's saying x is related to z, which is what you want to show to prove transitivity up here. Check. All right, so we get all three for this relation. All right, next one. This one's a little different. They don't give you a relation. They just say, suppose a given relation, whatever it may be, is symmetric and transitive. Is it reflexive? So you might sit and think about this. They don't tell you whether it's true or not. Typically, if I'm not told whether something is true, I either jump into some examples, or I just try to prove it and see if I run into a snag. Maybe let's just try to prove it. So proof, question mark, because maybe it's not even true. Suppose R is symmetric and transitive. I want to show it's reflexive, right? So I want to show, this is just a note to myself, I want to show that for all x, let's say it's on a set A. I didn't write A in the problem statement, but oh well. I want to show that x is related to x for all x. Okay. Well, how could I do that? I don't know. Let's pick an x and a. Right? That handles the for all statement because I'm picking an arbitrary x. How could I show x is related to x? I can't. I can't think of anything to do, at least. How am I going to use symmetry? I would need a y as well. How am I going to use transitivity? I would need x, y, and z. I suppose I could introduce those variables, but I don't necessarily see how I would leverage them. So at this point, I say to myself, maybe proving it's a bad idea. Maybe instead, I think I have to disprove it, in which case it should suffice to come up with an example. Right? And how big do we want to make our example? Let's see. For an example, I would have to pick a set A, and I would have to define a relation R. That relation would have to be symmetric, transitive, but not reflexive. Not reflexive means something's going to be missing from the diagonal. Okay, so right away, I know my diagonal shouldn't be full. So I don't know, let's start with like 2 elements. Right, that's almost as simple as you can get. I want it to be symmetric and transitive. I don't want it to be reflexive. Actually, now that I'm looking at this, I feel like the empty relation is good enough. The empty relation is not reflexive because it doesn't have the diagonal elements. But it is symmetric and transitive, vacuously. Of course, you might not think of that, right? That's weird. Vacuously true means, anytime you have a for all statement, with this sort of implication, right? If the assumption of the implication is like never satisfied, then the implication's true. So I think I might be getting that wrong, but I think vacuously the empty relation would be an example. But let's do something more interesting. Let's say I wanted, I need symmetry, right? So if I put a relationship here, I would need to put it here so that they're symmetric across that diagonal. Of course, that would be the only thing I could do because I need to leave the diagonal empty. Well, it's not sure. I suppose I could fill in one of these, as long as I don't fill in both entries on the diagonal. Then that's not reflexive because not every element is related to itself, just one of them is. But anyway, I don't necessarily need it. Let's see, this would be symmetric. Check. It would be not reflexive, which is what we're looking for. The question is then, is it transitive? Unfortunately not. It's not transitive, right? Because let's look here. I have 1 is related to 2, and 2 is related to 1. But transitivity would then imply that 1 is related to 1. But it's not. And of course I could add it in, but then by similar logic I would have to add in 2, 2. And then I would end up with a reflexive thing. Right? This would now become reflexive. So, okay, that doesn't mean I'm lost. It just means maybe I need a bigger set. Let's add a third element to A. So A is now 1, 2, 3 as a set. And I know if I'm going to include the things I included before, I'll still have to include them. So let's start here as a basis for our relation. And let's check if this is reflexive, symmetric, and transitive. It's not reflexive. Good, right? It's missing 3, 3. It still is symmetric, right? It's symmetric about this line. It has dots where it needs to have dots, and it's missing dots where it needs to be missing dots. Is it transitive? Actually, yes, it is transitive, right? If 1 is, let's color this a little differently. 1 is related to 2, 2 is related to 1, and then 1 is related to 1. I could do things on the diagonal too. I could say 2 is related to 1, 1 is related to 1, so 2 is related to 1. anyway, you can go through them all in your head and verify that it works. So this is a perfectly good example. I'll write the relation down as a set of ordered pairs. 1, 1, 1, 2, 2, 1, 2, 2. That satisfies the condition. Essentially, the logic here is if you have some symmetric and transitive relation which like leaves out an entire element of your starting set, then there's no chance for it to be reflexive, but it can still be symmetric and transitive. Cool. That indicates to me it was probably safe to just do something like this. But again, you get close to like vacuous definitions of what it means to be, it's not quite vacuous, but close enough, what it means to be symmetric and transitive. Okay. So cool. So that's a false statement. We successfully disproved it. Now, this is the true version of the statement. So you can change the statement. Say, okay, relation R is symmetric and transitive, so same assumption there. But additional assumption that for all elements of your base set, there exists something related to it. Right? That's exactly the opposite of what I just said about how, you have some empty row and column. Now it's saying there's not emptiness. Then reflexivity is guaranteed. So we're going to prove that R is reflexive. That proof will go like this. Let A be in A. My goal is to show A is related to itself. And right off the bat, I can use the hypothesis that there exists an X related to this A value. ST meaning such that A related to X. So that's just by assumption we can do that. Hopefully we can now use our other assumptions. I have one assumption that R is symmetric, so the fact that A is related to X should imply that the reverse is true. X is related to A. And now, transitivity saves the day. A related to X and X related to A implies that A is related to itself by transitivity. So I guess I'll write that formally. A related to X and X related to A implies A related to A by transitivity. Ta-da! That's our goal done. Right, since that's true for every element of A, R is reflexive. Cool. Okay, so what are these things that are reflexive, symmetric, and transitive all at once? Well, they're equivalence relations. They come up often enough in math, in fact, they're all over the place, that they do have this special name. So a relation R on a set A is an equivalence relation if it has those three properties. Furthermore, you can define what's called an equivalence class for a given element A, if you have an equivalence relation on the set A. The equivalence class of A is going to be just the set of all elements related to A. So I can write that in set builder notation like I highlighted in red right here. And great, we can start talking about what these look like. It's hard to sort of appreciate the definition without examples, so let's dive in. This one's kind of a beefy one right off the bat. Consider the set GL2R. That's a typical naming convention. This stands for, GL stands for general linear. Linear in the sense that we're thinking of linear algebra and matrices. General, I don't know exactly where that comes from, but it has to do with the matrices being invertible. So I guess most matrices are invertible, so there you go. That's general. Okay, so to lay this out, this is the set of all invertible 2x2 matrices with entries in R. That's why the real numbers are sitting there. And I can define a relation, I'm going to call it tilde, on this set by saying two matrices A and B are related if and only if, by the way, sometimes people don't write if and only if, they just write if, but it's taken as a definition, so it's intended to go both ways. If and only if the determinant of their product is positive. Is this an equivalence relation, and if so, what are the equivalence classes? Well, let's check. So we'll need to check reflexive, symmetric, and transitive. Reflexivity would say that a matrix is related to itself. So let's take some arbitrary invertible matrix, call it A. Since it's in GL2R, I know it's invertible. So since A is invertible, what do we know about the determinant of invertible matrices? We know the determinant has to be non-zero. That's one of the many equivalent conditions for being an invertible matrix from the invertible matrix theorem. Okay, so the determinant's non-zero. How is that useful? Well, let's think about what we want. We want to show that A is related to A. I.e., I want to show determinant of A times A is positive. So let's start thinking about determinant of A times A. Well, that's the determinant of the matrix A squared. And important fact, the determinant is multiplicative. So this is the determinant of A times the determinant of A, or written differently, the determinant of A squared. And what do I know about squaring things that aren't zero? You always get something positive. So that's bigger than zero. Hence, A is related to itself. Check. It's reflexive. Okay. Is it symmetric? Well, let's pick two matrices in GL2R and say they're related. Suppose A is related to B. I want to show B is related to A as well. Then, well, what does that mean? That means det AB is positive just by the definition of the relation. So, what about det BA? The determinant of BA. Well, again, the determinant is multiplicative. It's determinant of A times determinant of B times determinant of A. And now real numbers commute with each other. Right? The determinants are real numbers, so it doesn't matter which order I multiply them. And then we undo the multiplicative property of the determinant to write this as det AB, which we know is positive by assumption. So, ta-da! Hence, B also related to A. Symmetry holds. How about transitivity? This one might require a little more thought. As always, you can start by, picking three elements of your set, in this case, three invertible matrices, and supposing the first is related to the second, and the second is related to the third. We want to show the first is related to the third for transitivity to hold. Let's just write what this means. That is, det AB is positive, and also det BC is positive. How on earth am I going to get to something involving the determinant of AC? I can think of a couple ideas, perhaps. Perhaps. One idea that comes to mind, and I didn't have this planned in advance, so we'll see if it works. One idea that comes to mind is if I know something about AB, I know something about BC, and I want to link A to C, what if I just smash all those matrices together? AB BC. But I left a gap there because that's not like the most useful thing. Keep in mind, this might not end up working, but I hope it does. What if I now, I kind of want to get rid of these b's, right? I just want a and c left. So what if I multiply by the inverse? We know they're invertible matrices. They have inverses. So I could look at that. Right? That's equal to AC. So great. The thing I'm looking for is determinant of AC. I can write that as the determinant of AB, B inverse, BC. And then I have multiplicativity. Right? This is det AB. So I'll separate them into pairs. B inverse, determinant BC. Great, right? I know this guy's positive. I know this guy's positive by assumption. How about this guy? That's basically part A, right? Determinant of B inverse squared is the determinant of, or the squared determinant of B inverse. That's positive because determinant of B inverse isn't 0. Product of 3 positive numbers, positive. That's actually much cleaner than what I had planned. If you want a different way to prove this, so it is transitive, if you want a different way to prove all of these statements, so alternative, because it's fun to see different ways of proving things sometimes, you could observe that this condition, that the determinant of a product of matrices is positive, is equivalent to saying the determinant of A and the determinant of B have the same parity. That is, they're both even or both odd. And you can prove all 3 of these results using just that. And yeah, I mean, you may need the multiplicative of the determinant a little bit. I'm not sure. I don't remember, but great. Okay, so either way you want to do it, you get that this is an equivalence relation because it satisfies all 3 properties. What are the equivalence relations? What are the equivalence classes? Typically, the best way to come up with these is to just start with an element of your set and see what it's equivalent to, right? So what's a nice matrix I could start with? Well, I could start with the 0 matrix, but that's not invertible. So what's a good invertible matrix I could start with? Maybe the identity matrix, right? The identity matrix is invertible. So the equivalence class of the identity matrix, here capital I means the identity matrix with 1s on the diagonal and 0s off it. Well, let's just write the definition. That would be the set of all matrices in GL2R that are related to the identity. So A is related to I. What does it mean for A to be related to I? It means the determinant of their product is positive. But A times I, well, that's just A, right? So the equivalence class of the identity matrix should be this set. It's actually written quite nicely now. It's the set of all positive determinant matrices. That's a lot of matrices. You might suspect the other equivalence class will be something like matrices with negative determinant. And sure enough, let's write that out in set builder notation. Det A less than 0 means negative. What's an example of a matrix with negative determinant? Doesn't matter which one you pick, just come up with your favorite. Maybe I just make one of the entries negative and then keep it like the identity matrix. Cool. Yeah, and you can verify that works. And that exhausts all possibilities. Everything else, every matrix is either going to be positive or negative determinant. We know there are no 0 determinant matrices in GL2R because by definition, everything in there is invertible. So those are all my equivalence classes. Cool. Next one. Define a relation on the integers by a is related to b if the sum of their squares is even. Same questions. Let's go through it. Reflexive, yes, it is, right? Because for all integers a, I want to check if a squared plus a squared is even. Guess what? That's 2a squared, and that's 2 times an integer. Ta-da. So check. How about symmetric? Let's pick a and b. Actually, this one's sort of just immediate. Any integer pair. If a squared plus b squared is even, well, guess what? B squared plus a squared is even. Say one being even implies the other is even as well. Right, and this is saying b is related to a, so a related to b implies b related to a. Let's check. Transitive. Let's write this out as like a proof in English, because typically by the time you get to transitivity, things get a little uglier. So pick 3 integers, and suppose a is related to b and b to c. I'll just shortcut it and be like, that's a squared plus b squared is even, and b squared plus c squared is even. We want to know if a squared plus c squared is even. Well, what could we say? I know these two are even, and I know the sum of 2 even numbers is even, so I could imagine adding those two together. But of course, I wouldn't get equality then. Again, I'm going to do this sneaky thing where I insert something in the middle. What do you think I could insert? Well, I have 2 b squareds I want to get rid of, so subtract 2b squared. So, okay, hopefully we agree this term is equal to 0, so we do get equality here. And then what do we have? Even, those two are by assumption. And looky here, negative 2b squared, that's even because it's a multiple of 2. So it's the sum of 3 even integers, therefore it's even. That means a is related to c, so it's transitive. So we have another equivalence relation. What are the equivalence classes? Again, imagine just pick a nice integer to start with. What's the equivalence class of 0? Well, it's the set of all integers that are related to 0, i.e., okay, so a is related to 0. That's the same as a squared plus 0 squared is even. But a squared plus 0 squared is just a squared. So it's the set of all integers whose square is even. What do we know about integers like that? Well, the square of an integer is even if and only if that integer is even. So this is actually the set of all even integers. You might then suspect, what about the set of all odd integers? And I'll let you guys sit down and verify this one if you want. But it turns out that's the equivalence class of 1. Right? I'll give you a little hint, right? That's the equivalence class of 1 is the set of all integers such that a squared plus 1 is even. But that means a squared is odd. So hopefully that gives you an idea how to show that. And every integer is even or odd. Those are the only possible equivalence classes. We're done. All right. Let's go back to something more theoretical. So again, pretend I hand you 2 relations and I don't tell you what they are. Can you tell me something about their intersection and their union? Is the intersection of two relations a relation? Equivalence relation. Is the intersection of two equivalence relations an equivalence relation? Let's just pretend it is and see if we run into a problem. Okay, so I want to pick some arbitrary element of this relation I'm considering and ask if x is related to itself by that relation. Well, I know that R is an equivalence relation. So at least it's true. Let me write this down. Since R and S are equivalence relations, it holds that x is related to itself by R, and x is related to itself by S. Right, so this is a little different. We're juggling two relations, so I'm using different notation for each, but hopefully that's all right. Does this mean that x is related to itself in the intersection of those two relations? Well, yes, and it's easier if you write this in terms of ordered pairs. X being related to x means x comma x is in the relation R. Similarly, for x being related to x in the relation S. And what do we know about and statements for inclusions? Well, that means x comma x is in both R and S. It's in their intersection. Hence, x is related to itself by this new relation we're talking about. Check, it's reflexive. It's going to turn out to be both symmetric and transitive as well. I'll just preemptively put a check mark next to symmetric. Why is it symmetric? It's basically the same logic, right? So maybe I'll skip this and let you guys fill in the details. But the idea is going to be, if I suppose, so I'll write the first statement here. Let's pick x and y that's in the intersection of R and S. And what do we suppose? Right, you always want to suppose x is related to y if you're proving symmetry. Remember, we want to prove something about the intersection relation. So x is related to y by that intersection relation. What does that mean? Well, again, write it in terms of ordered pairs. X, y is in the intersection. And I think you guys can finish it from there, right? That would mean xy is an R and xy is an S, so blah, blah, blah. And you can apply symmetry of each of those to get your result. And then transitivity starts much the same way, ends much the same way. So A is true. The intersection is an equivalence relation. And then I'll spoil part B by saying it's false. Why is it false? Well, it suffices to just come up with a counterexample. Again, I'm going to do this by imagining a grid. And I want to take a union of two equivalence relations. So right off the bat, if I know I have equivalence relations, I need the diagonal filled. And I need symmetry among them. So this is going to heavily restrict what I can draw here. Let's say, I don't know, it's probably nice to start with at least 3 elements, so we have some stuff to work with. So this is my set A, it's 1, 2, 3. And I'm drawing A cross A. What do I want my relation R to look like? Let's say R is colored purple and S is colored red, just so I have some way to distinguish them on this graph. Well, let's say R has they're both going to have all the diagonal, right? So let's just go ahead and include that for both. Sort of overlap the purple and red, or imagine they're overlapped. Great, but I want to make it so that their union is not an equivalence relation. So I need to add some more things over here, because right now their union is just the diagonal, and that's an equivalence relation. Let's go back to R. So the relation R in purple, maybe I put this dot in, but then it's symmetric, so I have to put this dot in. So we're just constructing this counterexample by, trying randomly and abiding by the rules we have to abide by. Still not good enough, right? If I take the union of purple and red, I just get purple, and purple is an equivalence relation. I want to break the equivalence relation when I take the union. Maybe I do something similar to red. Maybe I toss a couple points on here. That guarantees symmetry. You can sort of check, it takes a while, but you can check these are also transitive. Now the question is the union transitive? So let me write these down. R looks like it's the set of ordered pairs 1, 1, 1, 2, 2, 1, 2, 2, and don't forget 3, 3. S is the equivalence relation. Well, it has 1, 1, and then it has these 4, so that's every combination of 2 and 3. Great. Their union, I will say, is not transitive. Why? Well, I need to pick two pairs of points for which transitivity fails. And I can pick, let's see, I could say that 2 is related to 3, and then 3 is related, maybe that's a bad one. 2 is related to 1. Now I'm thinking I messed up. I'm thinking this is transitive. Let's think about this. Basically, my goal is the only thing I can really look at is one of these spaces. I want to show that 1 is not related to 3 by this union relation. So I would have to start with 1 is related to something, blank, and that thing is related to 3. And these have to be the same number. So I could say 1 is related to 1, but then 1 is not related to 3, so that wouldn't work. I could say 1 is related to 2, and then 2 is related to 3. There it is. That does work. I just had to sit down and work it out. Right? 1 is related to 2 because this dot's in the union. 2 is related to 3 because this dot's in the union. But 1 is not related to 3 because this dot's missing. So there we go. Let's just write that down. 1 is related to 2, and 2 is related to 3, but 1, well, I could write this. 1, 3 is not in the union. Right, and you can check, it doesn't appear in any of these. Cool, okay, so unions do not preserve equivalence relations, but intersections do. Kind of interesting. Okay. Then, this is the big daddy of chapter 11. Theorem 1, so I'm skipping the partition definition, we'll go back to it. Theorem 1, if you have an equivalence relation on a given set, then the collection of all equivalence relations, the collection of all equivalence classes partitions the set you're working with. This is perhaps unsurprising if you look at previous examples. For example, this was an equivalence relation that partitioned the integers into evens and odds. I haven't defined partition yet, but it just means every integer falls into one of the equivalence classes, and they don't overlap at all. Right? Evens and odds don't overlap, and every integer is even or odd, so that counts as what I'm calling a partition. Similarly, back to the matrix example, all the matrices got partitioned into those with determinant greater than 0 and those with determinant less than 0. There's no overlap there, and those are the only options. Remember, we excluded non-invertible matrices with determinant 0. Similarly, you could look at the partition resulting from congruence mod 2. Okay, so we'll do that in a second. Let me just give the formal definition of a partition. It's a bit beefy. So given a set A, so forget about equivalence relations for right now. This is just a definition of partitions. So given a set A and a collection of non-empty subsets of that set, you have yourself a partition if the union of all those subsets gives you the whole set. Right, so you're imagining here's A, and maybe I've chunked it up into A1, A2, A3, A4, A5. Right? Then the union of all of those gives me A. So for it to be a partition, there can't be like any chunk missing from the collection of subsets. It has to cover all of A. And second, all of these sets have to be mutually disjoint. That's what this condition says. It says whenever you have two different indices, so like 3 and 2, they have to be disjoint. Right? Their intersection has to be empty. So I'm not allowed to, bleed over from one into the other. That would not be a partition. A partition is a division of your set into non-empty, non-overlapping subsets in such a way that you cover the whole set that you started with. Okay, so that's our formal definition. What is the partition resulting from congruence mod 2? Well, if we divide an integer by 2, we are left with two options for what the remainder is. Right? You either have remainder 0 or remainder 1. If it's remainder 0, that means you got an even integer. Right? If you divide by 2 and there's no remainder, guess what? Your number was a multiple of 2, so you're even. If you have remainder 1, that means, well, you were 1 off from an even number, you're not a number. So the partition of Z resulting from this equivalence relation is evens and odds. This equivalence relation, I'll write it out, I suppose. You could have -2, -1. I'm going to do this in a sort of instructive way. 0, 1, 2, 3, 4, 5, ... This is a list of all the integers. Here are the evens, here are the odds. And sure enough, these are also, that's the equivalence class of 0. And this is the equivalence class of 1. So yeah, not only do you have a partition, but theorem 1 sort of comes to our rescue and says, equivalence mod 2 is, or congruence mod 2 is an equivalence relation, so it has to result in a partition, and there's this beautiful connection between the two. Similarly, if I did this mod 3, you would get 3 columns for remainder 0, remainder 1, remainder 2. That's 3 equivalence classes, still partitioning the integers, and you can keep going from there. What if your friend tells you they found a certain equivalence relation on the real numbers, and the equivalence classes are these exactly? Is it possible that they're correct? Or can you guarantee that they're lying? Well, let's think. We're thinking about the real number line, going off to infinity in either direction. And we have some integers on here. Just draw some of them in. Here's 0, 1, 2, 3, etc. They're telling you that, well, this collection of intervals includes, the closed interval from 0 to 1, the closed interval from 1 to 2, from 2 to 3, 3 to 4, etc., and going this way as well. This is the thing, this is the collection of subsets he's handing you that he claims are equivalence classes for some equivalence relation. What do you think? Well, he's lying. Or he's wrong. I won't say he's intentionally misleading you, but he's definitely wrong. Your friend has made the fatal error that these supposed equivalence classes don't partition the real line. Sure, they keep going to infinity in either directions, and they end up covering all of R. But remember the second condition for a partition to hold. They are not allowed to overlap. And look at all this overlap. Okay. So you could say to your friend, well, if you made this an open parenthesis, maybe you're correct. But as it stands, or you could make this side an open parenthesis, but as it stands, this is guaranteed to not be an equivalence relation on the real numbers, because such an equivalence relation would have to partition them into non-empty, non-overlapping subsets, and your subsets, your equivalence classes, overlap. Which is kind of cool. You can just eyeball, a hypothesis and immediately tell it's incorrect, without knowing what relation they even thought they brewed up. Okay. How about, let's go a step further. Here's a different partition. This is a partition of Z. Right? You can see that every integer gets hit, positive n, negative n, 0. And there's no overlap. You're just pairing each number with its negative. Or in the case of 0, negative 0 is basically positive 0. So, okay, it's a partition. Can I reverse engineer this partition and come up with an equivalence relation for which that theorem above holds, that the equivalence classes are exactly the elements of the partition? So, again, you can think of a number line. Here's 0 on its own. Here's negative 1 and 1, negative 2 and 2, negative 3 and 3. Keep going. And we're saying, this is an equivalence class. This is an equivalence. This is an equivalence class. This is an equivalence class. And another color. 0 is an equivalence class all on its own. I'm trying to just highlight two integers individually, or one in the case of the number 0. What relation does that look like? Well, let's make some guesses. Could it be that the relation is this? N is related to M if maybe if their sum is 0? Right, that seems to work, because negative 3 plus 3 is 0, negative 2 plus 2 is 0. And within an equivalence class, the elements better be related to each other. It doesn't work. Take a minute to think about why it doesn't. Pause the video if you need to. The reason it doesn't work is because it fails to be reflexive. Right? Is 1 related to itself? No. Not according to this relation, at least, because 1 plus 1 is 2. It's not 0. And we know equivalence relations need to be reflexive. So this would not be reflexive. It would not be an equivalence relation. So let's just get rid of it. Okay, how could I fix that? I still need 1 to be related to -1, but I also need 1 to be related to itself, and -1 to be related to itself. Again, take a minute to think if you like. I'll write down a relation that works. N is related to M. If they're equal in absolute value, right? Absolute value is sort of like taking, the negative half of this number line and folding it over onto the positive part. And the great thing is, absolute value of 1 is still 1. Absolute value of -1 is the absolute value of -1, right? It's perfect. And you can check, you could say the equivalence class of 0 would be the set of all integers such that n is related to 0. According to our definition, that means absolute value of n equals absolute value of 0. Of course, absolute value of 0 is 0. And what's the only integer with absolute value 0? It's 0. So, ta-da! There's that element of the partition. Right? Equivalence classes should partition. The equivalence class of 1, similarly, is the set of all integers such that absolute value of n equals 1. But now there are two options. Absolute value of -1 is 1, and absolute value of +1 is also 1. Ta-da! And you can kind of go through and verify the others. So that's an equivalence relation that gives you the partition stated in the problem. Cool. Section 11.5 expands on the idea of congruence mod 2 that we talked about previously, and considers congruence mod n, and then defines a new set, which is the integers modulo n, and it's defined as a set of equivalence classes. Weirdly, you can add and multiply the equivalence classes here, in the sense that I could say, for example, if I'm working in the integers mod 5, then the equivalence class of 2 plus the equivalence class of 3 is the equivalence class of 5. And it turns out, if I'm working mod 5, that's the equivalence class of 0. This all turns out to be true. It might help to look and think about what we're doing here as think of these equivalence classes as sets. The equivalence class of 2 mod 5 would be, 2, but also -3, or I could add 5 and get to 7, etc. Just keep adding or subtracting multiples of 5. The equivalence class of 3 would be 3. If I subtract 5, I get to -2. If I add 5, I get to 8, ... keep going. And you can sort of see if I add these, 2 plus 3, for example, is 5. But also, -3 plus -2 is -5. -3 plus, 7 plus 8 is 15. 2 plus 8, for example, is 10. Where's another good one? 2 and -2 is 0. Yeah, basically you get all multiples of 5, which is the same as this set. This is the set of all multiples of 5, which is the same as the equivalence class of 0. Right? The equivalence class of 0 is everything that's 0 mod 5, but that's all multiples of 5. -5, 0, 5, etc. So yeah, in a weird way, you can add these sets together, not in a union-y type way, in a literal, like, add them element by element kind of way, which is sort of wacky. But yeah, any two of them you add together, you'll get a multiple of 5. And then similarly, you can do things with multiplication. You can sit down and play around with that yourself if you like. In any case, this is effectively a partition of the integers into n equivalence classes. Under the equivalence relation congruence mod n. It's a very powerful thing that'll come up in so many future math classes. So let's do some calculations with it just to make sure we're comfortable. Let's say we're in Z7, so we have the integers mod 7, so we get remainders of 0, 1, 2, 3, 4, 5, 6. So there's 7 equivalence classes there, depending on what your remainder is, mod 7. Doing these calculations, we can just see that you just add it like normal, but then you take your result mod 7, so 7 mod 7 is 0. Similarly, 13 plus 8 is 21, but 21 is a multiple of 7, so 21 mod 7 is 0. So these are the same equivalence class in Z7. How about 5 times 5? Well, that would be 25. Again, I can work mod 7. So I subtract a multiple of 7, say subtract 21, and I get equivalence class of 4. How about this? This looks beefy. Pretend we don't have calculators, and we don't want to do long division, because that's annoying. It turns out you can also reduce this mod 7 and this mod 7 before you multiply them. Right, so 702 is 2 more than a multiple of 7. Right, this is 700 plus 2, and 700 is a multiple of 7. So great, that's remainder 2. How about 355? Well, 350 is a multiple of 7. It's 50 times 7. So that's remainder 5. 2 times 5 is 10. Again, I can just do remainder 7 or remainder mod 7 as much as you need to. That gives you 3. Yeah, so multiplication, addition, all that jazz is pretty nice in the integers mod n. You can also sit down and write rules for how to add and multiply these things. So Z5 would have the elements 0 through 4. Technically, I should write brackets around these, but that's going to get old really fast. So let's pretend these are equivalence classes, and I'm just writing them without brackets. And let's see what we get when we add and multiply all of them. Well, adding shouldn't be too bad. 0 plus anything is itself. So I should just get a row of that and a column of it as well. This is, for example, saying 3 plus 0 is 3. Even mod 5 it is. How about if I add 1? Well, 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 is 4, 1 plus 4 is 5, but we're doing this mod 5, so 5 winds back to 0. 2 plus 1 is 3, 2 plus 2 is 4, 2 plus 3 is 5, but that's 0. 2 plus 4 is 6, but 6 mod 5 is 1. And you can almost fill this out by pattern at this point. Sit down and verify those are correct if you like. How about the multiplication table? 0 times anything is still 0, even if we're thinking mod 5, so let's just fill these in. 1 times anything is itself, so even mod 5, because these are all less than 5, this still works. Then 2 times 2 is still 4, even mod 5. 2 times 3 is 6, but that's 1 mod 5. 2 times 4 is 8, but that's 3 mod 5. Also, we should get symmetry here, because multiplication is commutative, so I can go ahead and put those in. 3 times 3 is 9, but that's 4 mod 5. 3 times 4 is 12, which is 2 mod 5. Symmetry gives me that. Then 4 times 4 is 16, which is 1 mod 5. So you can put these things in tables, and there you go. What ends up being interesting, and this won't be interesting in like a proofs class necessarily, but if you go on to take abstract algebra, in particular group theory, what you'll see is that this actually forms a group under addition. You don't have to know what a group is. Essentially all it means is every row and every column, there are no repeats. You get unique entries in every row and column. Pretty cool. Furthermore, if you ignore the zeros here, everything inside the red box is also a group under multiplication, because you get unique rows, you get unique columns. So this turns out to be a very useful set. Let's think about some weirder sets, though. Let's say I move to Z15, so integers modulo 15. And suppose I have A times B as equivalence classes equal to 0, and I'm, again, technically I should probably write that as the equivalence class of 0. Sometimes people get a bit hand-wavy with these, me included. Is it necessarily true that one of them is 0, right? This is sort of extending the notion of if the product of two numbers is 0, then one of them has to be. Is that still true mod 15? You might suspect it is, but it's not. Can we come up with an example? Well, if you think about 15, it's 3 times 5, right? So maybe I just say pick A equals 3, B equals 5. Then it's true that the equivalence class of A times the equivalence class of B is 0, because 3 times 5 is 15, but 15 mod itself is 0. But neither of these is 0. Right? This guy is definitely not 0, this guy is definitely not 0, mod 15. So this is another thing that'll come up if you ever study group theory. These are called like zero divisors, numbers that multiply, or objects that multiply, and give you 0 despite the fact that neither one is 0. That gives you some pretty weird groups in general. And that's about it. The last thing in the book in this chapter is just relations between different sets. So instead of having a relation just on a set A, you can define a relation on from one set to another. And then instead of being a subset of A cross A, it's a subset of A cross B. This is sort of just building up so that you can expand into the world of functions, where a function can be thought of as a subset of A cross B as well. Right? A function from A to B is sort of like a subset of A cross B. And maybe you've never thought about it like that, but sure enough, if I have, let's say I take arctan or something. That's a function from the real numbers to negative pi over 2 to pi over 2. And sure enough, this curve I drew is also a subset of R cross that open interval. Right? It's this point, and 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 this point. It's like infinitely many points, but it is a subset of the Cartesian product. So anyway, no exercises for 11.6, just an important notion to help you build up to understanding functions in the future. So that's it. Thanks for watching, guys, and good luck in all your math.